Okay. So hello, everyone. Thank you all for coming. Today, in our online mathematical physics seminar, we have Tatsuya Daniel talking about a time-varying cosmological constant from dynamical Chern-Simons gravity. So without further ado, you can take it away.
Okay. Yeah. Well, thank you very much for having me again this semester. I really enjoyed coming here in the fall and talking about giving an introduction to my research on quantum gravity and dynamical Chern-Simons gravity. Today is meant to be part 2 of the talk that I gave in December, at the beginning of December. So kind of the overview of what this talk is going to be. So the first part of it is going to be reviewing what I talked about in the first part of my talk, in particular with the canonical formulation of GR and the Wheeler-DeWitt equation. Those of you who were around for part 1 may remember that I stopped when I got to I mentioned Ashtekar variables at the very end. That was kind of where I ended. So I'm going to just go through again the canonical formulation, the Wheeler-DeWitt equation, because that's kind of the essential part of how we get to the Kodama state ultimately, and this Kodama state is what this work is focusing on in particular. And then of course, then I will talk about the new things in part 2. In particular, now that we are equipped with this background on second quantization specifically, and canonical formulating a canonical quantization, I should say. Then I will talk about dynamical Chern-Simons gravity and combining GR and DCS, and then talking about results specifically for this particular project. And if you have questions at any point, just feel free to interrupt me. Okay, so I'm gonna start off by talking about approaches to quantizing gravity. Okay, so what's the story here? You may have heard, because I know there are undergrads here, you may have heard that general relativity is it's not compatible with quantum mechanics. If you take general relativity and you do this canonical quantization procedure that I talked about in the fall, if you just do that procedure naively, you will end up with a quantum theory that is it's not normalizable, and it's also not renormalizable, meaning that you get unwanted infinities in your theory, like integrals that diverge. For example, when you take the norm squared of a quantum state, and so that's what it means to be not normalizable, and you also can't renormalize it. So renormalization is the process of basically removing unwanted infinities in your theory. It turns out you can't do that with when you just naively quantize GR. And I explained, I kind of walked through this procedure of why that's the case in the first part of my talk. Why that's the case. But anyway, so this is a perturbative statement. So what happens is that perturbative quantum gravity is not normalizable. So typically what happens is that you say that that quantum gravity, that we assume some sort of metric, and then we will perturb about that metric. And that's where this kind of non-renormalizable statement comes in. Well, the reason why I make the statement that this is applicable in the perturbative case is because there are also non-perturbative approaches to quantum gravity. So an example would be loop quantum gravity, causal dynamical triangulation, spin foam. So these are examples of non-perturbative approaches. Again, the exact, what those exactly are is not important for this talk, other than the fact that it's what we call a non-perturbative approach. And these attempts to yield a self-consistent quantization of gravity. These have difficulty in making contact with semi-classical limit. And I should mention that a lot of these non-perturbative approaches, they're what we call background independent. So they don't assume a space-time metric. And this is something that if you remember part one of my talk, when I was walking through why, if you take GR and just naively quantize it, why that theory is not normalizable, part of that was because you have this metric in there. But with these non-perturbative approaches, you don't assume any background metric. So in the canonical quantization of gravity, what we will be doing is we will be solving what's called the Wheeler-DeWitt equation. So this is a Hamiltonian constraint. Solving this Hamiltonian constraint will give us the ground state of our quantum theory. And the Wheeler-DeWitt equation, this Hamiltonian constraint, is that it's difficult to solve except in mini superspace approximations. Another word for mini superspace approximation is basically reducing down to FLRW cosmology, which, if you don't know what that is, it's the general metric that we use for cosmology, where we assume a homogeneous and isotropic metric. So anyway, this Wheeler-DeWitt equation is difficult to solve mathematically, except when we make this mini superspace or FLRW approximation. Okay, so that was just so giving you some introduction to kind of the approaches to quantizing gravity. So now I'm going to go talk a little bit, kind of review what I talked about in the fall regarding canonical formulation of GR. So just the canonical formulation. So just recalling what we do for canonical quantization. So in canonical formulation, you have a position and momentum variables that are typically denoted Q and P. So if you think to classical mechanics, even this is covered, for example, and these position and momentum variables, they will satisfy a Poisson bracket, and where a Poisson bracket is defined as such, and you can define the time derivative of your position and momentum variables based on your Poisson brackets with the Hamiltonian. Okay, so now when we quantize the theory, when we go from a classical to a quantum theory, we promote our position and momentum variables to operators. And so now instead the Poisson brackets, instead of them satisfying Poisson brackets, we go to commutators, and the position and momentum variables will satisfy some commutation relation. And the position and momentum variables are operators, so now they act on some quantum state, they act on a wave function. So, for example, if we take a position operator, we acted on a wave function that depends on the position, we'll get back the wave function, and it'll be multiplied by the position, and then the momentum will be the derivative with respect to the position of the wave function. And we end up with the when we promote our position and momentum variables in this way, we can write down the dynamics of the system, which is encoded in the Schrodinger equation. Okay, so when we talk about this in the context of GR, so the canonical formulation of GR is going to be Hamiltonian formulation. And so what we're going to do in this case is we're going to decompose our metric by slicing our 3+1 space-time into 3D spatial hypersurfaces. Okay, so we have we think about taking the norm, what it means to define a norm or norm squared with respect to some space-time metric. If you think just in GR, so now we're going to decompose this this norm. So what exactly are these terms here? So n, if you remember, so n is the lapse function. I'm going to be beta is what's called the shift function. I'm going to review what these are. It's you basically decompose the time coordinate into these lapse and shift functions. That's what these are. And then you have your gamma ij, which is going to be your spatial metric. That's the space-time metric that's projected out in the spatial direction. So again, so here's the schematic diagram of what this these lapse and shift functions are. So we can imagine that we have our 4-dimensional space-time, and we slice it we foliate it into these 3-dimensional hypersurfaces. So that's what these horizontal lines are. These are 3-dimensional hypersurfaces. These are space-like slices with the time being constant on these hypersurfaces. Then we see these dashed lines. So these dashed lines are time-like vector fields. So we can imagine that if we have a time coordinate and we are, it's along like the time like one of these time like vector fields. We call this T. We could decompose that into a component that is perpendicular to the space-like slices and a component that is parallel to the hypersurfaces. So the component perpendicular to the space-like slices, that is that is essentially the lapse function. Lapse function dotted lapse function with it dotted into the unit vector. That's just this n of a. That's just the unit vector, and then beta, unit normal vector, I should say, and then the beta, this beta of a, that's the parallel component of the time coordinate. So if I just write that out mathematically, I just take this t vector and I just decompose it into the perpendicular part and the parallel part. Okay, so when I apply this 3+1 decomposition to the Einstein-Hilbert action, so the action that corresponds to GR, I get something that looks like this. Okay, so now I have so this R, this is with respect to the Riemannian metric. So that's the Ricci. That's what we call the intrinsic, I guess, the intrinsic curvature. That's the Ricci scalar. This K, this is the extrinsic curvature. So the way you can think about intrinsic versus extrinsic curvature is intrinsic curvature is deviation away from a Euclidean. It's kind of just the deviation away from the kind of Euclidean kind of three-dimensional hypersurface. But it's, so that's kind of what the intrinsic part means. The extrinsic curvature means that you are taking your hypersurface and you're, so to speak, you are deviating that into other dimensions, higher dimensions, so to speak. So that's kind of this, like, again, this extrinsic versus intrinsic curvature is not super important for, especially when we get into the Kodama state. This part is super important, but these components of the extrinsic and intrinsic curvature, they both show up, just from GR, and then when you decompose it, that's what happens. You get this extrinsic curvature that's now a function of it's now a function of the lapse function that we've defined here, and then this beta, which is the shift function. Okay, so we have this Lie, we just have a Lie derivative here, and we have this L sub n. So the n is just the unit normal to surfaces of constant time. Okay, and then so like I said, we have these lapse and shift functions, and we can choose what our lapse and shift functions are. That's a choice of gauge. It's a gauge choice that we can make. So if we we can set n equals to 1 and beta equal to 0. And so then our Hamiltonian will look something like this, where again, gamma is that's our spatial metric. And then our pi here, this is the momentum conjugate to the spatial metric. And then we can recover Einstein's equations via Poisson brackets with H. So remember, in just when you have a canonical theory, you can define the time differentiation, basically the time variation of a position variable with its Poisson brackets with the Hamiltonian. So that's exactly what we're doing here to get Einstein's equation. So that's the equations of motion for GR effectively. So now I'm taking this quantity in parentheses, and I'm calling this G, capital G. So this is sometimes called the Wheeler-DeWitt metric. But when I do this, I get this this Hamiltonian here.
Tatsuya?
Yeah.
So when you say that we can choose the lapse and shift functions, that's equivalent to choice of gauge. Do you mean that we're like choosing a coordinates, or is this related to diffeomorphism invariance?
Yeah. So this is related. It's related to diffeomorphism invariance. So our lapse and shift functions, that's telling us how our time it basically tells us how we're decomposing our time coordinate. And if you think about it, right, it shouldn't be like, your theory should not be dependent on how specifically you're decomposing your time coordinate. And specifically, when you think about beta as being, that's the part that encodes basically the spatial variation. So if you think about the diffeomorphism invariance, which is essentially just a coordinate invariance, right? Your theory should not depend on, the coordinates, the specific set of coordinates that you choose. So that's exactly what this choice of lapse and shift functions That's what it relates to, is the diffeomorphism invariance. Yeah.
So in this Hamiltonian formulation, we're working with a specific time function, but the dynamics of the system should be independent.
That's right. That's right. Yeah, and you can see here that we have our spatial metric and we have our momentum conjugate to the spatial metric, which I've just written out here. Okay, so now, so now we have our quantized Hamiltonian. So now we start looking at the constraints on a theory. So we have a set of what are called primary constraints. All that really means in this context is that the conjugate momenta, they vanish on and off shell. Okay. On and off shell means that they satisfy. So on shell means that the classical equations of motion are satisfied, and then off shell means that they aren't. But the point is that the momenta vanish. We have additional on shell constraints, which are called secondary constraints. Okay, so one is the spatial. So one is the gradient of the spatial momentum. The other one, this is the more important one for in the context of the Kodama state, this h equals 0. And so the Wheeler-DeWitt equation, this is going to be what encodes the quantum dynamics of the system. So it's analogous to the Schrodinger equation, except that the time is actually not physical, so it becomes a constraint. So and the reason why the time is not physical is the time is not physical. We've decomposed the time, and we've made a gauge choice, which again, like I said, once you make there's a gauge freedom there in how you decompose your time. And when you get to when you write down the Wheeler-DeWitt equation, the time component is actually not physical. So that's so that's kind of where the analogy to the Schrodinger equation, why it's not exactly the Schrodinger equation. But anyway, so this Wheeler-DeWitt equation, it's so this constraint is h equals 0. If I write it more specifically, it's the Hamiltonian, this Hamiltonian operator that we've now defined, acting on this quantum state, this wave function that we're going to call psi, as a function of the 3 metric is equal to 0. So that's this Wheeler-DeWitt equation. Okay, so at this point, actually, I'll go into the Wheeler-DeWitt equation. This is kind of where we just were. So anyway, so the Hamiltonian constraint in quantized GR. So this is what we had before. So I'm just writing it a different way. But this psi here, and I'm writing in the Brockett notation. This psi here, this is the so-called wave function of the universe. This was first discovered by Jim Hartle and Stephen Hawking back in the 80s. So this is a functional differential equation on the space of 3D spatial metrics. And so this psi, when we write down this psi, this quantum state psi, so it's no longer, when we write it in this way, it's no longer a spatial wave function. In other words, it's no longer defined on a hypersurface. So it's actually now, it's a functional of field configurations on all of space-time. And so this quantum state psi contains all of the information about the geometry and matter content of the universe. And so this Hamiltonian, it still acts on a Hilbert space, but it no longer determines the evolution of a system. Okay, so using metric, so this is what I talked about last time. So using metric variables leads to some mathematical difficulties when you try and promote the classical Hamiltonian to a well-defined operator. So this is what happens is you get these like unwanted infinities, and and the Hamiltonian is actually not well defined when you try and write it in terms of the 3 metric spatial metric. So the Wheeler-DeWitt equation, this was originally written down in the 60s. But then there were about 20 years of no progress after it was written, because people just didn't know how to solve it. And then in 1986, there was a realization of, okay, maybe what if we tried writing down the Wheeler-DeWitt equation in terms of other variables? And so what happened then was that these, when you write down the Wheeler-DeWitt equation in terms of this other formalism or these other variables called Ashtekar variables, the Wheeler-DeWitt equation actually becomes well-defined. This was shown after this introduction of Ashtekar variables and the Ashtekar formalism in 1986. The following year, then Ted Jacobson and Lee Smolin showed that the Wheeler-DeWitt equation actually mathematically becomes well defined when you write it in the Ashtekar formalism. Okay. So at this point, I'm getting to kind of where I ended last time. So at this point, I'm going to pause here if there are any questions. If not, I will continue with Ashtekar variables and the Kodama state. So, okay, so then after Ted Jacobson and Lee Smolin showed that the Wheeler-DeWitt equation is mathematically defined with in the Ashtekar formalism, then what Hideo Kodama did in 1990, a few years after that, was then kind of built on the work of Ashtekar, Jacobson, and Smolin, and expressed GR. So I should say that the Ashtekar formalism expresses GR with a connection. So Kodama was kind of building off of this work. So you can express GR with a connection where we're going to now that's denoted as capital A, and its conjugate momentum defined as capital E. And now these satisfy these canonical brackets, this Poisson bracket relation. So now this is exactly analogous to, when we think about a canonical, starting with when we canonically quantize something, we have a classical theory that that has a position and momentum variables that satisfy a Poisson bracket. So that's exactly what's going on here. So now the connection is analogous to like a position variable, and this momentum here is capital E. Okay, so the Wheeler-DeWitt equation, like I mentioned, is not mathematically, even when you write it in the Ashtekar formalism, it's still like mathematically, it's still almost impossible to solve without making the mini superspace approximation. So without making this reduction to homogeneous and isotropic metrics. But when you do that, you can actually solve the Wheeler-DeWitt equation exactly using it in the Ashtekar formalism. And the solution is called the Kodama state. Now, I should mention that the Kodama state is a solution to the Wheeler-DeWitt equation for all metrics. It's not just mini superspace. In order to solve the Wheeler-DeWitt equation, you need to apply the mini superspace approximation to realize that you get something like a Kodama state. But the Kodama state actually solves the Wheeler-DeWitt equation in all cases. It's not just in the mini superspace approximation. Okay, so the Kodama state, it's because you can solve this Wheeler-DeWitt equation exactly. And I mentioned that solving the Wheeler-DeWitt equation amounts to finding the ground state of a theory, or a zero energy solution, or a state with the lowest energy. So if the Kodama state, it possesses a lot of these properties that we are familiar with from quantum mechanics with with a wave function. So this Kodama state we can think of as okay, it has some quantum mechanical, it has things from quantum mechanics that we know, so it's a good candidate for being able to describe quantum gravity non-perturbatively, because it's an exact solution. When we find the Kodama state, it's an exact solution to the Wheeler-DeWitt equation. So the Kodama state is a good candidate for being able to describe quantum gravity non-perturbatively, a theory of quantum gravity, but it does suffer from a number of issues. So one of the main issues it suffers from is non-normalizability. So the Kodama state is actually still not normalizable if you take the norm squared of the wave function that's not finite. It has CPT-violating properties, charge parity time violating properties that we don't like, just based on from what the laws of quantum mechanics and quantum field theory tell us. And it's also not gauge invariant under large gauge transformations. Okay, this last point is not super important for the rest of the talk, but I just throw this in there because it's one of the issues that like as far as like the Kodama state, not just being accepted as a theory that just it solves this question of quantum gravity, which is it's a huge question. It's people have been as you've seen, people have been working on it for decades, and it's also a very broad topic. I mean, there are many ways that people have tried to quantize gravity. And the Kodama state has come up, in the last 30 years as a good candidate for being able to answer some of these questions, of how do we quantize GR. But it has these issues associated with it. So that's where this work comes in, is looking at is there a way to resolve maybe some of these issues that the Kodama state has? And that's where dynamical Chern-Simons gravity comes in. So going back to GR, there are well-motivated reasons to consider modifications to general relativity. And this is something that you may or may not be familiar with, particularly for undergrads. Typically you just learn about GR, but there, of course, people do have considered, and it's a very active area of research where people do consider, okay, what if GR alone is not the full gravity theory? What if we have to modify it a little? And there are well-motivated reasons to consider modifications to GR. One reason is what's called anomaly cancellation. So this actually comes from string theory. So string theory predicts, string theory is, 10, depending on the type of string theory, but string theory will live in, typically 10 or 11 dimensions. If I'm thinking like heterotic string theory, for example, you don't have to know what that is, but that's in 10 dimensions. And the point is that string theory is actually what we call a UV complete theory, meaning that it doesn't have divergences at high energies. And we can now predict from string theory, we can predict what the gravity theory would be, what gravity theory, a certain string theory would predict when in 4 dimensions. And so the way you would do this is you do a process of what's called compactification. You compactify the extra dimensions from string theory in order to get to your 4 dimensions of gravity. And this, when you do that, you will end up with a gravity theory that looks like GR, but it has extra terms in it. It turns out these extra terms lead to another current that is not conserved. So you may know, if you've taken this is covered in classical mechanics, but also especially in quantum field theory, that if you have some Lagrangian, or if you have some theory, you can write down Noether currents associated with that, and these Noether currents would correspond to symmetries in your theory. It turns out that when you try and calculate a Noether current, and you calculate something that looks like d mu j mu, turns out that quantity is not 0, so you get a current that's not conserved. So this is called an anomaly, and so broadly speaking, anomalies, generally we want theories that don't have anomalies in them, especially local anomalies, I guess I should say. And so one way that you can cancel this anomaly that you get from string theory is by adding a term to GR, which is basically modification. That modification will cancel this anomaly. Okay, so this is one reason to consider a modification to GR. There are other reasons observationally. One example is that there's been recent observational evidence recently of a parity violation in the CMB. So parity violation is, you can think of that as spatial reflection, or like if you look in a mirror, the physics should be the same. So that's roughly what parity, like a parity transformation is. And so parity violation is this idea that the left and right hand, the left and right-handed physics of the universe don't behave. They aren't symmetric. You don't have this symmetric. You don't have this symmetry in the spatial reflection. So there's been recent observation of parity violation in the CMB, and also there's also this phenomenon of this lepton asymmetry, this baryon asymmetry in the universe. And one way to possibly solve that is you produce extra you produce extra baryons or leptons basically to resolve this like baryon asymmetry in the universe. So observationally, there are reasons why, and that this phenomenon of leptogenesis, this can be generated by an extra term in your action or in your Lagrangian, right? So if you have GR plus something else, that something else can be the source of this leptogenesis, and it can also help explain this parity violation as well. Well, a good candidate that can answer all these is a modification to GR called Dynamical Chern-Simons gravity. So it's a strong candidate that people have considered in the past. So for one, chirogravitational waves can possibly emerge from dynamical Chern-Simons gravity. So you may have heard of gravitational waves, and chirogravitational waves are just gravitational waves with a certain handedness. So there can be left-handed gravitational waves or right-handed gravitational waves. And the reason why chirogravitational waves are important is because that can be a source of parity violation. And so this can possibly emerge from dynamical Chern-Simons gravity. It can also be used to dynamical Chern-Simons gravity can also be used to, or I should say, chirogravitational waves can be used to resolve the argument that the Kodama state is not physical. So one of the main criticisms when the Kodama state was when it was formulated was the fact that it was just not physical. The reason is because there could be negative energy solutions resulting from that, unbounded negative energy solutions that correspond to negative helicity states. So that's something that actually Ed Witten argued about 20 years ago. And so for a long time, people thought, okay, the Kodama state is not really physical because it has this issue with negative energy solutions. Well, it turns out that you can actually reframe this this issue of negative energy, these negative energies in terms of chirogravitational waves that are, you can just think of it as a positive energy solution with the opposite handedness. So this is something that people started realizing only recently in the last, I think probably in the last, about 10, 15 years, I would say, people started really thinking about DCS gravity and chirogravitational waves. And then, with increasing observational evidence for parity violation, then DCS gravity started to become more attractive as far as a modification GR that people consider. Okay, so the next part, I'm going to talk about how we're going to combine GR and DCS. For now, any questions before I move on with that? Okay. Okay. So now the big question is, so can we still find an exact solution, like a Kodama state, to the Graduate equation by including dynamical Chern-Simons in the full gravity theory? So that's really the main question that this project was seeking to answer. So the starting action it's basically just GR. We're going to couple it to fermion fields. That's not very relevant for the main result. The main point is that we start with GR. We're going to do this 3+1 decomposition, and we're going to do this in the Ashtekar formalism. So let me just explain what we have here. So we have this integral again. So we're going to integrate out. We're going to integrate over time here. So we're doing a separate integral over time here. So that's this dt. Then we have this integral over sigma. The sigma, this is just the 3D spatial hypersurfaces that I mentioned. So you take your space time and you do this foliation into your horizontal hypersurfaces. So that's what the sigma is. Of course, we've got this E, so that's our momentum. This A, that's the connection, this A dot. All right. Then we have this N, this curly N, that's the lapse function. This H, that's the Hamiltonian constraint. This N, this N of A, that's the shift function. And then this D of A, this generates the diffeomorphisms of sigma. So that generates your right. So that generates along the hypersurface, right? That will generate your diffeomorphisms. And then the G here, this curly G, this is going to generate local gauge transformations. And then so that's this. So this part here, this first term, all in parentheses, that's what I talked about before, especially in the first part of the talk, was the first part of the talk in the fall, I should say, about doing this 3+1 decomposition, and this first term that was corresponding to GR. Then we get this extra piece here that's from dynamical Chern-Simons gravity, and you'll notice that you have this lambda here. This lambda, this is the cosmological constant. So that's associated. So that's associated with what we call dark energy. So that's associated with that's the term that we give for the reason why we observe that the universe is accelerating faster and faster. A reason that is associated with that is something called dark energy, and that's we call lambda here. So anyway, you see that we have this lambda dot over lambda squared, and then we have this integral over the 3D hypersurfaces of this Y Chern-Simons term. I'm going to explain what this is. But so we get this extra piece from dynamical Chern-Simons. That's the important part of this. Okay, so going through this process, so once we get this 3+1 decomposition, there's you can get the Hamiltonian constraint via a similar procedure that I've talked about before, but now we're just doing it in the Ashtekar formalism. So when you work it out, you'll get this you'll get the Hamiltonian that corresponds to GR. We have an F here, that's our field strength tensor. And then the Chern-Simons piece is going to look something like lambda dot over lambda squared, which we can write this whole prefactor multiplying the Y Chern-Simons. We can write that as theta dot. The reason why I write it that way is because typically when we introduce dynamical Chern-Simons gravity, that's associated with a scalar field. And this scalar field, so that's basically what this theta here is. That's the scalar field that we introduce when we add dynamical Chern-Simons in. And so we see that in the Hamiltonian constraint, we have the Chern-Simons piece, but it's now multiplied by the time derivative of the scalar field that we've introduced. Okay, so now we're going to apply our quantization procedure. So this is all classically. Okay, so now when we apply the quantization procedure, we're going to promote our position and momentum variables to operators. So in the Ashtekar formalism, that means that we're going to promote our connection capital A and the momentum capital E to operators. So what happens here is, so similarly, like we take momentum, and we can define that as the derivative of the position variable, with derivative with respect to the position variable. So we're going to do the same thing here. We're going to take E, and that's going to we're going to take that to become basically the derivative with respect to the connection A. So when we do that, we get now we can write down our full Hamiltonian here. So now this is now the full Wheeler-DeWitt equation. So before we just had, so the Kodama state is the solution to the pure GR, I guess. So the Hamiltonian constraint is the solution to, if we imagine we just get rid of this HDCS like we had before, just HGR times psi equals 0. That's what we had before. That gives you this Kodama state when you solve it. Okay, but now we have this extra piece here from Chern-Simons gravity. And so when we write it out explicitly, we got something that looks like the bottom line here. Applying this quantization procedure. Okay, so now just going through with solving that bottom line there. So now we're going to take this ansatz for our wave function psi, which is defined in terms of our connection. So we're going to define that to be psi of k, little psi of k. So psi of k, the psi k of A, this is the Kodama state corresponding to pure GR. And then it's going to be multiplied by some modification that we're going to call chi. That is going to be dependent on A, the connection. It's going to be dependent on the connection A, and then also the scalar field theta dot. And I've written out psi k of A here.
Tatsuya?
Yep.
I'm a little bit confused by kind of what we have written down in our ansatz. So we're writing psi k of A. So if I remember correctly, the idea is that our wave function is defined on it's like a functional, right? Is that so? It takes in a metric, and it spits out a number. So what is it? I suppose my question is, what does it mean for a functional whose inputs are themselves functions, what does it mean for it to be renormalizable? Um, you know, if I'm working with like a function in L2 of some interval on the real numbers, then I know what it means for that to be renormalizable. Um, I'm a
Yeah.
little confused on what we mean
So,
here.
so good. So good. So the wave function here now. So I've written the Kodama state as a function of A. So it's actually now not in terms of the three. It's now not in terms of spatial metric. It's in terms of A. So we're treating A as our. We're considering that to be like our position space now. So we would define the norm of this wave function in the connection space. So we would integrate this over like all possible values of the connection A. And so what happens is then for something to be, well, normalizable would mean that the norm squared of this wave function in the connection space, that, so you do this integral, right? That integral would be, for it to be normalizable, or I guess, yeah, for it to be normalizable, that would be finite. That norm squared would be finite.
Perhaps a dumb question, but I think it might be fun to ask.
Mhm.
Is there a way to move between connection space and metric space? Like how in orthodox quantum mechanics, we can move between position space and momentum space. Is there a similar thing going on?
That's a very good question, and so I'm going to get. So I'm gonna actually I'm getting to it. So that's actually what that's partly why we do. Actually, that's a big reason why we do the mini superspace approximation. Is actually when we do that, we move from this connection space to we move to a metric space. We move to the FLRW metric space, and so then that actually makes this. It makes well, first of all, it makes the Wood equation easier to solve, and then it also makes it easier to make it's easier now to make contact with what we observe, in cosmology. So as far as like, if you don't make that approximation, though, this is actually still something that is like an active area of research in this field specifically. This is a very niche topic, but like, people are still trying to figure out, okay, how do we relate the connection in terms of the spatial metric, particularly in relation to the Kodama state. Is there a way we can define the Kodama state in some way that we can actually make it obvious what the relation between the connection and the metric is in the generic case, like without the mini superspace approximation? Right. So we have this ansatz here. So what we're doing is, we're basically saying that our new Kodama state is going to be the pure Kodama, the GR Kodama state, the old Kodama state times some modification that we're going to call chi. So we make this ansatz here. We plug it into the bottom line of the previous slide. We get something that looks like this. So we get a differential equation in chi. So if the field strength tensor F, so we have this field strength tensor F that's here in the second term in parentheses. So if F is independent of the connection space, we get a modification here to chi to look something like that, like this. And then that means that psi again, so psi is just psi of k times this chi. So that's what our psi of A becomes. That's what the modification, the Kodama state becomes.
Sorry, I just realized maybe the question that I really should have been asking from the start. When we write psi k of A is like exponential of that thing on the right hand side. Is that defined in like a purely formal sense? Like it is because I'm not entirely sure what it means to take the exponential of the thing that we have. But if it's kind of coming from similar to the ODE that you have written down there, if it's coming from an ODE that's similar to that, then it would make sense.
So this solution here comes from an ODE that looks like this. Comes from so it's this. When you solve the top line here, so you take this GR Hamiltonian, multiply it by psi. Okay, so then it becomes, and then you take E, you do this quantization procedure. So these E's become D by dA. you end up with an ODE that looks something like what we have here. And so then when you do that, you get this exponential. So it's the same, so when we define it, when we say something is exponential to that, it's like in the same way, right, that you would traditionally solve an ODE. Okay, so it's more realistic to assume that if the field strength tensor is not independent of A, because if we think about what the field strength tensor is, it's it's usually it's the derivative of your, in this case, the field strength tensor realistically should be the derivatives of your connection variable, basically A. So it's more realistic to assume that the field strength tensor is dependent on A, right? So it's not independent. So if we make that assumption instead, the more realistic one, then we get this modification to chi. It looks something like that. And then of course we can solve for we can plug that in and find what psi of A is. So this right here is what we have. This is the modified Kodama state solution. Okay, so now here's where we're going to reduce to meaning superspace. Now here's, I guess, where Lawrence, your question here on where we make contact with the metric. So that's kind of where this comes in. So what we have here, so little b. Okay, so little b and little c, these are functions of time. Little a, this is the scale factor A of cosmology. So what happens here? So C is roughly C is equated to what's called torsion, if you've heard of that, and B here. So basically, the point is that when C is 0, when you say okay, there's no torsion, which is typically what GRs do. So torsion is that's not something that's included in, typically not included. That's like not included in GR, right? So torsion is like something extra that you include. When you set torsion to 0, so you say, okay, well, let's just not worry about torsion. Then roughly what happens is that this B here, this is approximately A dot. So you can roughly think of this little b as the rate of expansion, roughly. So B is that's the chain of A dot basically. And so we make this mini superspace reduction. So we're making contact now with FLRW cosmology. And when we do that, we can now write our wave function that was before a function of capital A. We can now write it in B space. So as a function of the rate of the expansion rate. So we get something that looks like this. Okay, so we get a commutation relation that so we can use this commutation relation between B and A squared. And when we do that, we can actually take the Fourier transform of what we have up here. We get something that's in A squared space. So the scale factor squared. So the reason why we have this is because, okay, we can, if we set C equal to 0, so again, no torsion, and we expand this exponential here. Expand the exponential. We'll get some expansion that looks like this. So I've written down the first term in the expansion here, and okay, we can plot the wave function in this in B space. So the important part here is that, okay, so the solid blue, that is the real part. So this wave function is it's complex. So the real part of the wave function here is that's denoted in solid blue, and the imaginary part of the wave function that's in dotted orange. Okay, so the important part here is that the wave function is actually not it's not divergent at the origin. It's finite. So this gets into another issue that I won't talk about, that I won't discuss in this talk. And that's something called the Big Bang singularity, which is the fact that the Kodama state actually traditionally blows up at this origin. And with this modification that we've included now from Chern-Simons gravity, it's at least in the case of no torsion, the wave function is finite at the origin. Okay, so now just a quick aside on Gauss diffeomorphism constraints here. I'm just going to go through these real quick. So the Kodama state also solves the Kodama state also satisfies the Gauss constraint and the diffeomorphism constraint in addition to the Will-Dewey equation. So there are two other constraints that the Kodama state has to satisfy. So I'm just going to write down the Gauss constraint. You can roughly think of this. So E actually, so this is the conjugate momentum, but you can think of it in this context kind of like the electric field, right? So the derivative of the electric field give you 0. And then the diffeomorphism constraint, again, coordinate invariance is right down here. So do these constraints hold when the Pontryagin term, so this is the extra term we add in to the Einstein-Hilbert action from GR from Chern-Simons gravity. So do these constraints hold when the Pontryagin term is included? So this is important. This is an important question because the Kodama state still needs to solve those other constraints in order for it to be, valid. So it appears so, but this is something that we actually need to investigate further because the Gauss constraint is actually going to be automatically satisfied due to, well, if you rewrite E in terms of the field strength test, you'll get something that's like D on F. So that automatically is going to be 0 for what we have here. And then the diffeomorphism constraint has to be satisfied due to the symmetry of the frame fields, which I write down here. So we get something that's like we get trace of like E, EJ, EI. So that has to be under the symmetric interchange of those frame fields. That has to be the same. And the only way that this equality is going to hold if we do the symmetric interchange is if this whole quantity is 0, which that is the diffeomorphism constraint. So that seems like the diffeomorphism constraint is satisfied due to the symmetry of the frame fields. And again, this is something we need to investigate further as far as the Kodama state still being a valid theory, even if it satisfies these constraints. Okay, and then one quick thing on the Chern-Simons time. So I mentioned that the time is not physical. So when we write down the Graduate equation, the time is actually no longer a physical quantity. So, and that's actually kind of one of the main criticisms of the quantum gravity approaches is that time is not something you can define. So you can actually define what's called a Chern-Simons time, which is just this integral over the Chern-Simons functional. Which the Chern-Simons functional that's basically it's just a function that's dependent on A here. It has a commutation relation. So this Chern-Simons time has a commutation relation with the scalar field from Chern-Simons gravity that we've introduced, and it's got this uncertainty relation that I have written here in terms of lambda instead of theta. So lambda and theta are actually related. So lambda and theta are inversely related. So lambda and the Chern-Simons time, they can be treated as classical variables if the expectation value of lambda is small. And so we can achieve this by tuning the Chern-Simons coupling such that it's sufficiently small. And then if we have the opposite case, then lambda and the Chern-Simons time are not compatible. Okay, so here I'm going to wrap up with kind of conclusions and where we go from here. Okay, so what exactly what exactly did we do? So we found an exact solution to the Graduate equation when including dynamical Chern-Simons gravity into the full gravity theory. So we still found the Kodama-like state. We evaluated the Fourier transform of our wave function when we reduced it to mini superspace. The main function of that was so we could be able to plot it and then see, is the wave function finite at the origin? Okay, so the scalar field introduced by dynamical Chern-Simons gravity, so this theta, it directly encodes the variation of the cosmological constant. So like I mentioned, so lambda and theta are inversely related to each other. So you can imagine that. So theta dot will go something like lambda dot over lambda squared. So the wave function actually still suffers from the normalizability issue. It's finite at the origin, so that so there are some indications that maybe this can fix some issues with the Big Bang singularity that the Kodama state has had, but it still suffers from this normalizability issue. So you can actually do this integral. You take psi of b that I showed in a previous slide, and you can do that integral over b space. The wave function is actually still not finite when you do the norm squared. That norm squared is still not finite. So it still suffers from this normalizability issue. So now the question is, an open question that for future work is, are there conditions in which modifications to GR will make the traditional Kodama state from pure GR normalizable? So this is something worth continuing to pursue. Approaches to gravity quantization with dynamical Chern-Simons gravity included. Especially given its how well motivated it is cosmologically and observationally, it's worth continuing to pursue. So with that, I will wrap up, and thank you very much for listening. Happy to take more questions.
All right, so before we continue to the questions, why don't we all just say thank you very much to our speaker for coming out and talking to us about his research today. Yeah, so why don't we open the floor to questions?
Yeah, sure.
So if you don't mind, I have a question mainly regarding the wave function that we plotted earlier.
Yep.
Right, so we said that we were plotting this on A space.
So this wave, this plot specifically is in well, yeah, it's in A dot space. So B is A dot. So this is actually an A dot space.
And the idea is the metric is being fully encoded by simultaneously A and B, or is it like is the idea that there's like a correspondence between A and B and the metric? I'm a little bit confused on what that
Yeah.
correspondence is.
So right. So the FLRW metric, if I write it in conformal time, it's something that looks like A squared times quantity minus D dt squared plus dx squared. So again, this is in conformal time. Which, okay, you don't have to know what conformal time means. The only thing is, the only relevant part is that, so the FLRW metric, it depends on A squared. And so A squared here is, if I go back even further, yeah, so A squared, that's, so what we're doing here is we're taking our conjugate momentum, and we're basically making that a function of A squared, of which the FLRW metric is based off of. And then B here, that's just that's A dot. So that's related to just the rate of expansion. And so then, from cosmology, you may know that, A dot over A is a quantity that we call the Hubble constant. So that's something that shows up in cosmology. So really what we're doing here is we've made a connection. When we go down to mini superspace, we're relating our connection variable, capital A, and we're relating those to the metric via A and B. So I guess so A and B are related to the metric, which we're now associating with capital A and capital E from our connection space.
So is there a sense in which kind of our wave function is not defined on the set of all potential metrics, but that we're really just considering this like family of metrics, which are corresponding to the FLRW regime? Or
yeah, that's right. So yeah, good. So that's right. So basically this wave function here, it's, well, okay, so this psi of B, this is defined exclusively on the space. So it's a specific, right? So it's it's homogeneous isotropic metrics, right? So it's a very specific family of solutions. And I should specify, so one thing I kind of glossed over was that, so this integral here, it's, so the Kodama state, it's in the context of what we call path integral formalism. So what's really happening when because the Wheeler-DeWitt equation is actually a functional differential equation. So what's really happening is you are integrating over the space of all possible metrics. So when we reduce to mini superspace, we're restricting ourselves to a certain family of metrics on which the Kodama state is defined. Now, when we write it in terms of big A, so the connection to that connection. So now we say that the wave function is actually defined. It's defined on all of, on the connection A. So in theory, it's defined on the space of any possible metric in theory. Now what happens is that, so the trick is doing this path integral. This actually becomes difficult in the generic case. Like mathematically, it doesn't become, like, it's just difficult to define that in the generic case. It's easier in the Ashtekar formalism, and that's why we are using it to write the Kodama state, because before, when we just write this in terms of the three metric, then it was just not mathematically defined in general. So now we have something that's mathematically, it seems to be well defined. It's still difficult to write down in the generic case, though, at least when we're relating it to the metric. So that's why we do this mini superspace, and then we have something that's exclusively defined on that space of metrics.
Okay, yeah, I think that makes that definitely gives me a much clearer picture of kind of like the things that we're dealing with here and like the tools that we're using. So would you say that like the wave function that's coming out of this is supposed to give you some sort of probability density on the well, yeah, so I suppose I'm asking, is it giving you some sort of probability density, or is this going to suffer from not necessarily having a conserved current? And then that also leads to the question of, does it make sense to talk about a conserved current on this space of metrics?
Yeah, those are all actually, those are all very good questions. So roughly speaking, so you can associate a probability. So when we make this mini superspace reduction, you can associate the wave function, the psi of b, with some probability density. So that's what we had before. So one of the important reasons why this is finite at the origin, why that's important, is because now there's actually a finite probability of it not diverging, right? So now there's some finite probability that it'll be at 0 basically. So right, you can associate a probability density with this. It's difficult, at least in the mini superspace approximation. In the generic case, it's a little bit more it's a little bit like we're still not entirely sure of what it actually means necessarily. Like it's still like some sort of like probability density. Like you're saying, okay, if we were to plot psi of big A, we would be saying, okay, we're looking at what is the probability that our psi is going to be at some value of A, right? But exactly what that means physically is not, like, it's a lot less clear in the generic case. So it's a little bit more difficult. It has, it's got an interpretation that's something like that, but it's, as far as it's saying like the probability density exactly, it's still like kind of not, still something that we're actually not, like the community in general is not actually sure on that idea. Now, as far as your other points, so yeah, it's,
I think my question was flawed, and I kind of realized that now, because our wave function is not a function of time. It's just a function on this metric space.
Exactly. Yeah.
Which means it doesn't make sense to talk about a probability current because the probability is not flowing anywhere. It's in, I mean, it doesn't even make sense to say it's stationary. It's just, if you take a probability interpretation of it, then what we'd be saying, I guess, and correct me if I'm wrong, but it would just be saying this is the probability that your universe is given by this specific metric. And that's like a global thing.
Yeah. Right. So yeah, because we don't have, it doesn't make sense to talk about probability currents because this is not like the wave function is not defined on, it's not a function of time. We're defining it on this connection space. So there's no notion of probability flowing from one configuration to another, if that makes sense, right? So yeah.
Yeah, this is interesting. This definitely clears up some conceptions I have about this notion, and it's really great to see just a relative, it's a formal definition, but an explicit solution written down in this way to the wave functions that we're working with.
Yeah, which, I mean, that was the main result of this paper, was showing that, okay, when we have this extra modification, we can still write down we can still actually find an exact solution that we can, a closed form expression that we can actually write down. That's kind of the main, that was the main result of this paper, showing that, okay, even if we, when we include Chern-Simons gravity, we can still write something like this down. And it seems like it may be able to solve some of the issues mathematically that the Kodama has had. So that's why this is definitely worth continuing to pursue. Is it possible that some modifications like this could resolve some of these issues with the Kodama state? And if it does, that might give us some insight into the classical theory. Like, okay, so does the classical theory actually need to have this Chern-Simons piece in it? So it's not just GR. Does it need to have this Chern-Simons piece, or does it need to have other terms in it as well? So definitely interesting to keep studying.